Welcome back to another video in Dwsim. So the last time I showed you how to install the software and open it. So this time you're just going to go directly to the simulation. So today you're going to focus on the Rankine cycles. This will be the ideal Rankine cycle and the actual Rankine cycle. So let us begin. So what we're going to do is going to create new under process modeling. We have the setup like this. So our working fluid will be just water. So going to click water, enter, and then we add it. Once you see there's a tick, go to next. We go to I want to select specific property package, which will be steam tables. Scroll down to steam tables, next. So what I say is I'm going to use SI engineering. That will give us temperature in degrees Celsius, pressure in bars, instead of having the SI units of temperature in Kelvin and pressure in pascals, because we're going to be dealing with pressures that are very large. For example, 30 bars, that's like 30 million pascals, and I think it's much more better if you see it in bars. So what we're going to do first, since we're dealing with a Rankine cycle, we will first import the material stream, click and drag it, double click to make it in view, click it, and now I'm going to change this to be our inlet. So we know it is water, so there's no need of saying it's water inlet. Then we go here, we say what properties are we going to be dealing with. From the previous video we just dealt with the temperature and pressure, so our specified variables will be temperature and pressure. So to compare with the Carnot one, the temperature was at 360 degrees Celsius at a pressure of 30 bars. Once we've done that, we click now, we continue down to accept and update, because that's what we're going to delete today. So from the inlet we go to the turbine. You'll find it in the pressure changes, in the expander. Click it and it will automatically connect. If it doesn't, then just click the turbine, go to the connections, and the inlet should be whatever you have named over here, the outlet should be here, and the energy stream I think it will show itself over here. So in order to make all of this in view, double click the template, or even drag these, then double click again to make them all in view. So click the turbine and we go to properties, change this to turbine instead of being X1. Then what we're going to say is we want to deal with the outlet pressure. We want to calculate the outlet pressure. The thermodynamic path should be adiabatic, explained why in the previous video. The outlet pressure, let's say, to be 5 bars, like just the same as the Carnot engine. 5 bars, adiabatic efficiency of 100, and this to be 100, and that's it. From there we are done with the turbine. What we're going to do is let's click this one and rename it to, let's say, step. Let's say the steam, say just the turbine exit, So from there we need to condense this liquid, since it's going to be a loop and we care about the enthalpies. So unlike for the Carnot engine where we just dealt with the efficiency dealing with the temperatures of the inlet and the outlet of the turbine, in Rankine you're going to deal with the efficiency, the overall efficiency of the entire cycle, and that will deal with the enthalpies. So first we need to take this steam and condense it purely. So I do not know, let's try to see, calculate it first. So press F5 or press this, and you can see here, click the turbine exit, go under the results and see that the fraction, the vapor fraction, is 0.99. Whether you use this one, let me double click this, whether you use this one or you use this one, it's just the same. So you can see the vapor fraction is 0.99, which means it's very, very close to vapor. Majority of this mixture is vapor and some little bit of liquid, which you can see here 0.0077. So first, in order to go to the pump, because I think that's the difference between Rankine and Carnot. Setup wise, it is a pump involved. So the pump works only with liquids, pure liquids. So you need the fraction to be the quality. Let me say the quality to be 0, to be purely liquid. And how are we going to do that? We're going to use a condenser or a cooler. So how are you going to do that? You're going to use in the exchangers. In the exchanger, you're going to use a cooler over here. And since I'm using this version, it automatically connects. So in this cooler, what do you want to do? What do you want it to do? Since we want it to be purely liquid, what we care about is the outlet. So what you're going to do is go to the cooler, you go to the properties, and rename this to be our condenser. I think that's why most examination use condenser, and calculation mode will be the outlet vapor fraction, because we do not know the amount of heat removed from the liquid. We do not know the temperature of that liquid at that specific pressure, unless you go to the steam tables and find it yourself. But since we're using a software, it only already has the tables. So what we care about is we want it to be purely liquid. So what we want to go the calculation mode to be outlet vapor fraction, and the outlet vapor fraction over here should be 0. That means purely liquid. Don't do anything over here, it will calculate it by itself. Also, this is an isentropic heat removal. I do not know exactly what it's named, but this is the isentropic removal of heat. So the pressure drops should be 0 and efficiency should be 100. I mean, it's isobaric cooling, I think so. So yeah, so the pressure should be the same, so there's no pressure drop, but the temperature should reduce, and that will be determined by the vapor fraction. Once you're done with that, so after the condenser, we go to, I'm just going to click over here, we go now to the pump, and where the pump is in the pressure changes. So pump, click it and drag it. So in this case, as you can see, it has its own inlet and outlet, but you want the inlet to be this one. So what you can do, click the pump, go to the connections, the inlet to be, then this is much better if you rename this inlet, this to be pump inlet. So we go to the pump, and the inlet should be this one, pump inlet, connected. This will be disconnected, and we can just delete it. So right click it, delete, click yes. So as you can see, the turbine, from the turbine to the condenser, from the condenser to the pump, and you can see there's an energy stream. This energy stream is pointing towards the component, which means it will be inputting energy to the pump. This is different from the turbine, which is pointing away from the component, which means that the component is giving us the work. So now from the pump we go to the boiler, since we want to raise the temperature from whatever is going to come out from the condenser to whatever is going to enter the turbine. So what do we need a boiler from? The boiler, will find it from the exchangers, and that will be a heater. As you can see, automatically it has connected the pump outlet and the turbine inlet automatically. If it does not do that, click the heater, go to the connections, and select whatever you need. So here we're going to name it from 6 to be pump outlet. and you're done from there. So what is the work of the pump? The work of the pump is raising the pressure but maintaining the temperature constant. So it is an isothermic compression, I think so, or isentropic compression. Whichever it is, we want the temperature to be the same as that is exiting the condenser. So we click the pump and we say the efficiency to be 100%. This is an ideal Rankine cycle, and the calculation mode should be, just name this to be pump. Calculation should be the pressure increase, not the pressure increase, the outlet pressure. So we want the outlet pressure to be the same as the one entering the turbine, 30 bars. We click that. So now it is entering the turbine like so. So then from there, the heater, we go to the heater, we go to click these ones to take you to the properties. So let's say this would be a boiler, and calculation mode should be the outlet temperature. We do not know the heat required to raise the temperature of that liquid from a certain temperature to 360 degrees, because we want the liquid to be, not the liquid, the working fluid to enter at 360 degrees. So the calculation mode should be outlet temperature, and our outlet temperature should be 360 degrees Celsius, efficiency of 100%. Just make sure all the efficiencies in the properties are 100%. Condenser properties, efficiency 100%, pump work, pressure, efficiency of 100%. Now, as you can see, it is in red, which means it has not been calculated. Double click everything to be in view. You can also resize some things to make it larger. So what do you need to do? Either press F5 or this. And as you can see here, there is a problem. It just said that infinite loop detected while obtaining flowsheet object calculations. Why? Because you can see this is a loop. Inlet the turbine, exit inside the condenser, into the pump. Let me move this to make a few bit of sense. Inside the pump, then to the boiler, then back to the turbine. And this will cause a loop. And in such cases, you cannot connect like that. So what do we need? We need a recycle block. Just say please insert our recycle blocks where needed. So what are you going to go? You're going to go to the logic blocks and find recycle block. Drag it over here. As you can see here, it has its own inlet and outlet. So what are you going to do? So first we will disconnect the boiler. So the outlet, we click this empty space. You have disconnected it, and we say that the outlet should be now this 5. So it is connected to here. And now you'll disconnect inside the recycle block. We disconnect this outlet. We do not want to be 6, we want it to be inlet. And so we have done so. So delete this. So as you can hear, as you can see, from the boiler it goes to the recycle block and then the inlet. So whatever as you can see here, there's a dotted line showing that this is a loop, yes, but first it goes to a recycle block, telling this simulation that you want to see a loop. That's the only point. You want to see a loop. So what I'm going to name this could be inlet 1, just to make the visually the aesthetic to be good. So now we can do this. We can now run it again, and voila, as calculated, it is now in blue. So first of all, you're going to see some things. You can see that inlet single compound stream detected. This means that it's only one compound, that is just water, and now switching to pH flash. This is not a problem. It's just telling you that you've switched the calculation formulas and other stuff. Same to inlet 1 single compound stream detected. Switching to pH flash, there's no problem. It's good. You can see it has been calculated very, very well. And now we can go to discuss some things over here. So as you can see here, for the turbine, the energy stream is pointing outwards, meaning the turbine is outputting energy. It's giving us energy. Same thing to the condenser, there's an output here. For the pump, there's an input of energy, it's pointing towards the pump. Same case to the boiler, there's an input of energy here. Let me discuss some things over here. So for the condenser, this heat rejected, the heat rejected from the condenser is the latent heat of vaporization. But in this case, since we're condensing the fluid, it's the same thing, but now it's the latent heat of vaporization. Why? Because we're changing, as you can remember, let's select this turbine over here. The results, you can see the vapor fraction was 0.99. So it was partly vapor, mostly vapor, and partly liquid. But you want it to be fully liquid. So we need to condense that vapor. And the condensation takes place at the same temperature. It's just that a lot of latent heat will be removed. And that is what we have over here. We're not going to use it. It just tells us that a lot of energy has been removed from the liquid, from the mixture to form a liquid. And from there now, to increase the pressure from 5 bars, remember the outlet, it was the properties, it was supposed to, the outlet pressure is 5 bars. Now to increase the pressure from 5 bars to 30 bars, it's done by the pump, and that requires work. So you can rename this energy stream from E3 to pump work. Pump work. Pump work. And also you can rename this from E1 to turbine work, or work done by the turbine. The work done by the turbine. And then we are going to focus on this. Now this is the heat required, or the heat input, the heat added into the liquid to form it a vapor, to form a vapor. So we're going to use this. And now to find, as you can see, this is everything you're going to need over here. As again, I can even that can show some of the properties very well. We're going to go to the setup, and we go to flow sheet settings. Scroll down to, you want to see the temperature, you want to see the pressure, and that's it. So after that, you can see now everything in view. Instead of clicking the properties one by one, you can clearly see everything. So I'm just going to move these things about so that you can see them clearly in the units specified. So as you can see over here, the inlet of the temperature of the turbine is 360 degrees at 30 bars. The outlet is 151. So this is calculated why? From the pressure outlet. We say the pressure outlet to be 5 bars. So using steam tables, it checked the pressure outlet at 5 bars. So it was 151 degrees. Then it checked if it was superheated. If it was not, then it went to saturated and found that the vapor fraction is 0.99. The quality is 0.99. It's very good. So it is high quality. And then it goes to the condenser. As you can see, the temperature between the condenser and the pump inlet is the same. It's isothermic, just removing the latent heat of vaporization at the same temperature and at the same pressure. 151.84 degrees, 151.84 degrees, 5 bars, 5 bars. Now it enters the pump as a liquid. This is what the latent heat of vaporization, the energy removed, rejected, it shows. Now it is purely liquid, vapor fraction of 0, or the quality of 0, and increased the pressure to 30 bars. It increased the pressure at 30 bars. So as you can see here, a little bit of energy has been added in form of temperature. As you can see, there's a slight rise of temperature. So over here, it's either we check the properties and say the efficiency of everything is 100%, because ideally I think should be the same, but let's just see. I think, yeah, no, yeah, the pressure increases, then this is now the temperature of that liquid at 30 bars. Now it enters the boiler. Now we want this liquid to be purely vapor, and to be purely vapor at a certain temperature, 360 degrees Celsius. So if our calculations in the boiler, the properties was the vapor fraction wanted to be 1, then I think this should have changed. This should have changed. But since you cared about the temperature, we say that you want it to be 360 degrees. This ensures that at 360 degrees and at 30 bars, it is purely vapor. And this is the energy required by the boiler. So we're going to rename this to be heat added. Heat added by the boiler. 2496 kilowatts. And it has been risen from 152 degrees to 360 degrees at the same pressure, 30 bars. Then it goes to the turbine, and it's a loop. So this R1, or this recycle block, shows it's a loop. Now from there we need to calculate the efficiency of the ideal Rankine cycle. It is ideal because every component over here has an efficiency of 100%. 100%. So how are we going to do that? So first, we need to find in the calculations that in the calculations, I'm just going to use ChatGPT over here because I do not have time to type it. So this is the calculations of finding the efficiency in a Rankine cycle. You ignore this part of the real whatever. So for a Rankine cycle, so it is the work done by the turbine minus work done from work required from the pump divided by the heat added in the boiler. Or else you can use the enthalpies of the working fluid. So the enthalpy H1, H2, work here, H4, H3, H1, H4. So in order to visualize that very, very well, we can just name the flow sheet to the inlet to be number 1. Let's just say into brackets number 1, inlet of the turbine, outlet of the turbine to be number 2. So come over here, click it, number 2, and then from here outside the pump it should be number 3. And then here it should be number 4. As you can see here, just the same thing, 4, then 1 again, then 2, then 3. So using ChatGPT, it just said that you're going to use the spreadsheet to calculate the efficiency, since you cannot find it directly. So what it just said, it has said that the efficiency of a Rankine is H1 minus H2 minus, into brackets, H4 minus H3, into brackets, H1 minus H4. So what does this mean? I think it's much better if you say it's the work done by the turbine, which is H1 minus H2, the enthalpy in the inlet minus the enthalpy outside, then minus work required by the pump, which is just H3 minus H4, inlet of the pump, outlet of the pump, H3 minus H4, divided by the heat added by the boiler, this one, or just H4 minus H1, or H1 minus H4, so that can be a positive value. And when you do that, you get the efficiency. But I think it's much better if you find the work done by the turbine minus the work required by the pump divided by the heat added. You're going to use that instead of using the enthalpies, even though it shows the enthalpies over here. It's either you copy paste it or just use it simply away. So go to the spreadsheet and you say that you want the work required by the turbine. So work done by the turbine in kilowatts. Enter. Just need to resize this, and I'm going to put it over here. So what I'm going to do is I'm going to import data from a material stream, and it's the turbine, not material stream, the energy stream. Yeah, it's the work done, so it's the energy stream. Don't know why I'm not finding it. Energy stream, the work done by the turbine, the energy flow in kilowatts. So there are all of these units. This kilocalories per hour, BTU, this is British thermal units per hour, BTU in seconds, calories in seconds, HP, this is horsepower, horsepower, or kilojoules per hour, megajoules per hour, kilojoules per day, megawatts, watts, BTU per day, I don't know what that means, but what we focus is in kilowatts. Okay, then we enter. So you can just resize this so that you can see the full value. It's 407 kilowatts. Next, what do we need? We need the work required. So double click, work required by the pump in kilowatts. And the same thing, we right click this, we import data, the energy stream, it's the pump work, energy flow in kilowatts. The next thing we need is the heat added in the boiler, heat added by boiler in kilowatts also. So it's either you choose kilojoules per kg or kilowatts. Since our energy is in kilowatts, we're going to use that. So right click this, import data, energy stream, because we're dealing with energy, or the work, energy stream, heat added, energy, kilowatts. Okay, now this is what you have. Now in order to find the efficiency, just write here efficiency, double click, efficiency, what have they said? It will be, double click it, I mean this one, it's not as smooth as Excel, but equal sign to, so it is work done by the turbine, that is B1, minus work required by the pump, that is B3. All of this divided by the heat added by the boiler, which is B5. Enter, and you get this is the efficiency. So we can get the efficiency in percentage. Just write it over here. Efficiency in percentage. So just the equal sign, we reference this cell, which is B7 multiplied by 100%. Now it is 16.22%. Now this is the maximum energy, the maximum efficiency of an Rankine cycle. Because it's an ideal Rankine cycle, this is the maximum energy, maximum efficiency for the Rankine cycle. And you can see it is smaller than the efficiency of a Carnot cycle. The Carnot cycle, as I try to recall, it was 32.87% or 88%, 32.88%, and here we can see it's 816.22%. The same inlet properties of 360 degrees Celsius and 30 bars, the same outlet properties of 151.84 degrees Celsius and 5 bars, but now this is going to be the maximum efficiency you can ever get for a Rankine cycle, and you can see it is always smaller than the Carnot cycle, which means it follows the rules or the laws of thermodynamics. So in order to find this, instead of going back and forth the spreadsheet, once I've populated it, you can just go to the objects and say add new linked spreadsheet table, double click it, the cell range should be spreadsheet, so you come here, select this, and you copy this A1 to B9, so write it A1 colon B9, and now we go to the flow sheet. I've written exclamation instead of one, enter, and now it has populated it. So this is everything in the spreadsheet, showing us the work done by the turbine, the work required, the heat added, the efficiency, and the efficiency in percentages. There are also some things, for example, like the steam properties. I don't know if it's the work ratio. So the work ratio can be done using, I think that's okay, spreadsheet. The work ratio is taken, double click it. These are just other properties you can just add. For example, the work ratio, the steam consumption. So just write whatever you want to write. The ratio is dimensionless, so there's no units. And what you just do is so how can you find the network or the entire network of the entire cycle? So to find the net work, it will be, let's say, net work or work net. That's much better. Work net. It is the work done by the turbine equals sign B1 minus the work required by the pump, or work done by the turbine plus work done by the pump. Now since the work required by the pump, it will be a negative sign, so I'm just going to write it exactly what I needed, because the work required by the pump is already positive, so I'm going to use the negative sign. But when you talk about the work added and work rejected, the work rejected by the system is always, it is positive, and the work required by the system is negative. So what I can do here is write the work rejected plus, into brackets, the negative, because it should be negative, of the work of the pump, which is the work required. So since the sign is always going to be negative or minus, so instead of doing all that stuff, just do it minus, then B3. Now this is the work, the net work of the system, which is 404 kilowatts. Forgot to write kilowatts. Expand this. So this can also be used in the formula. Instead of writing B1 minus B3, you can just take the work net divided by the heat added. It's just the same thing. It's just that you have went directly to the components themselves. So the work ratio is equal to work in the system, E1, divided by the work done by the pump. Yes, it should give you something 0 point something. And this is correct. This is very good. And actually this is very, very close to an ideal Rankine cycle of the work ratio of 0.99. So the next thing is the steam consumption. So it's the specific, let's forget to double click then specific steam consumption into brackets SSC, which is also the mass flow rate of the steam divided by the work output. So I mean the work net, the work inside the system. So if the steam the mass using the SI units, the mass flow rate is in kilograms per hour, so we need to change that. So in our case, I have to change it to kilograms per second so that you can get the it's the mass flow rate in kgs per second. That will be this mass flow rate in kgs per second, which will be, we need to import it or just write it. I think writing it's much better. 2600 kgs per hour divided by how many seconds are in an hour. That's 2600, and all of this now it is divided by the work net, which is now E1, and I think we need to rise it. Let's remove this 2000 and just write it the way it is in hours already. I think I've messed up over there, so this would be the mass flow rate. This is the mass flow rate. The mass flow rate is in 2600 kgs per hour divided by the work. Then this is now our specific steam consumption, and the units is in kgs per kilowatt hour. So what does this mean? It means that for every kilowatt hour you need to get, or for every kilowatt for in 1 hour, you will consume 8.889 kgs of steam. So therefore, the lower the specific steam consumption, the better. It means you're getting more energy for a little amount of steam. And how can you do that? You can do that either by increasing the temperature, the inlet temperature, and when you increase the inlet temperature, you can either do that, let's say to at 400 degrees, and let's run it again because sometimes it says some things that are wrong. So when you increase the temperature, since it has reduced it, so what can we do? Instead of changing over here, let's change it in the boiler. Let's say the outlet temperature of 360 degrees, and I mean the outlet temperature, then the outlet temperature to be 400. Calculation mode of the outlet temperature in the boiler, and then run it again. Since there's something wrong over here, then run it again. Yes, so it said when it said something wrong, it means that something else was using the properties of the inlet, and that will conflict. So for example, if the turbine was expecting 360 degrees previously and you've changed the boiler, then there'll be some calculation inconsistencies. So we run it again to force it to be 400 degrees, and as you can see, it is 400 degrees over here. So since it's 400 degrees, same pressure, same temperature, the efficiency has actually dropped from 16. I don't know what it's doing. I don't know why it keeps don't know why, because something is definitely wrong over here. Something is very wrong. So just going to return to it was 360 degrees. and run it again. Run it again. So yeah, so over here I think what you can do is change the properties of the. So what can we do here? You can either reduce the pressure to be at least 1 bar over here, then you press play, and as you can see here, the efficiency has increased to 24% from 16 to 24%, and the specific steam consumption has reduced from 8 to 5.32. so the lower the steam consumption, the better, and it also increases the efficiency proportionally. So in order to include this, just double click this and increase the range. The range is all of this, so A1 to E13. Oh really, E13? Yeah, so A1 to E13. So flow sheet, we come over here from A1, then colon to E13. Enter. Yeah, so this is now the entirety of the spreadsheet. So just demonstrating that you can either do this by reducing the pressure of the turbine, which means there's a much larger pressure difference and therefore much larger temperature difference, because 1 bar corresponds to 99.61 degrees. As you can see, I'm using 1 bar, but the pressure at sea level is 1.01315 bars, so that's why the temperature is slightly smaller than 100 degrees. And as you can see here, the vapor fraction is likely for today. Let us just return it to where it was, the pressure to be 5 bars, so that it can be the same as that for Carnot. And run it again, 16%, 8.88. So as you can see, I've demonstrated that the Carnot engine is the most efficient, it will give us the maximum theoretical efficiency. This is an ideal cycle, so this is what you're going to get. So to make it an actual Rankine cycle, so what you're going to do is just sum efficiencies in the properties of all the engines. So you can just say the efficiency of the boiler is 75 or 80%. Let's say 80%. Same case for the turbine. The adiabatic efficiency is 80%, and also change this. The condenser also, the efficiency is 80%. The pump also, you can say the efficiency is 80%. And run it again, and you can see here, let's run it again just to make sure. You can see here, yeah, as you can see, I'm like running it multiple times, so just to make sure everything is being calculated well. So when you run it again and see there's nothing changing over here, then the system is stable. Now you can see the efficiency dropped because there's some efficiency drop from each and every component. The steam consumption has increased, meaning that for the same kilowatt per hour we'll need more steam consumption than an ideal Rankine cycle, and it conforms to the laws of thermodynamics, since this is an actual Rankine cycle where there's some efficiency in the turbine, efficiency in the condenser, efficiencies inefficiency in the turbine, inefficiencies in the boiler, in everything, and it will accumulate and see that the total efficiency has dropped from 16% to 10%, and the specific steam consumption has increased from 8 to 11%, and also the work ratio has decreased from 0.993 to 0.9895. So yeah, so this has demonstrated both the ideal Rankine cycle and the actual or the real Rankine cycle. If there is any other question, please write them in the comments. So, and we are done. Previously I did not show you how to save the flow sheet, so what to do is file, save as. We can write it as Rankine cycle. For me, I have a lot of videos, or not videos, a lot of files named as this. So Rankine cycle, and note where it is saving here in the note this place, because this is where you're going to find them. Note them, this is where you're going to find them. You can also change it. You can select the folder you want to change it. For example, in my thermodynamics, let's say cuts and assignment, and save it over here so you can find them. But since I know where it is saving, I will just return it back to where I know, because I know where it is saving. But if in case you do not know, note of this, change the folder if you cannot remember, because in order to find them, then if you do not remember the folder, then you have to come back to the software, try to save something even though you have not done anything, and copy the file location, this part, copy it and try to search it, because most everything is here. Even these, the ones that are not here, these are just examples, so remember where you have saved them. So I'm going to say this, and everything here is done. So I think that's everything that we have done for today. We have tackled on spreadsheet, linking spreadsheet,